because we write a function to the left of its argument. That means we write fx, where f is the function and x is the argument. To the left of the argument we write the function. That's why this whole thing happens. I mean, it has to be adjusted in that way. And this usage is traditional. Oh, I should mention that. Write a function to the left of its argument traditionally. It looks odd because we traditionally write a function to the left of its argument. This may be confusing at first. There is one alternate notation where the function is written to the right of the argument. So instead of fx, some more ink is needed. Instead of fx, we would write xf. This, however, has been proved more confusing than clarifying. Well, this line is of course the author's opinion. I don't think it is really confusing. When you write the function like this, when you write functions like this, you just have to keep in mind what you are writing, that's all. So it is his personal opinion. He doesn't like this, so he has written it has been proved more confusing than clarifying, and he writes something else also, which is true nonetheless, and has not yet become particularly popular. Okay, so personal tests aside, we go to the next definition. So this is definition 14. It's a very important thing, one-to-one function. 1 to 1 function. A function f from x into y is said to be 1 to 1, or it has another name, injective, if for all elements x1 and x2 in the domain x1 not equal to x2 implies fx1 is not equal to fx2. That is, you recall the remark that we made previously that when we started the video today, well, it may not be today because this may be another part, right? Anyway, the remark that we made in the beginning when saying that functions obey the axiom of substitution, there we said that if two inputs are equal, then the outputs must also be equal. However, we mentioned that unequal inputs don't necessarily imply unequal outputs. But if that happens, if unequal inputs imply unequal outputs, then such functions are said to be one-to-one or injective functions. So in one-to-one function, two different inputs will never have the same output. Okay, the arrows won't come like this. They are one-to-one, not many-to-one. Okay, or in other words, the same condition can be written in a different way. Since this is an implication, instead of writing this, I can write its contrapositive also. In other words, let me write it here. fx1 equal to fx2 implies x1 equal to x2. These two implications are basically the same thing. They are logically equivalent and contrapositive of one another. This is P implies Q. This is negation of Q implies negation of P. Now there is an example illustrating this class of functions. And this is again informal. We could have created some examples using only natural numbers, but nonetheless, this type of examples will be dealt with more later on when we develop the integers and real numbers. So that's why we are prematurely considering them, in spite of the fact that we haven't developed them yet. So the function f from the set of all integers into the set of all integers defined by fn equal to n square is not one-to-one. Okay, this function is not one-to-one because you already, you can understand why it's not. The distinct inputs -1 and 1 have the same output 1 under f, because square of minus 1 is 1, square of 1 is also 1. So this is not 1 to 1. On the other hand, the function g from n into z, now we have considered a smaller domain, not the entire integers but only the natural numbers. Given by the formula is same but the domain is different. As such, the functions are different. Keep that in mind. Is 1 to 1. So changing the domain changes the whole thing. So the notion of one-to-one function depends not only on what the function does, but also what its domain is. So this is the notion of a one-to-one function or an injective function. Injective is adjective, of course. Such functions are sometimes called injectional. And after this, of course, we have the notion of an onto function, but before that there is a remark. And this remark is also important to keep in mind. I mean, it tells you the condition that you should be looking for when you want to show that a function is not one-to-one. If a function f from x to y is not one-to-one, then we can find distinct elements. Okay, the elements are different, they are distinct. X and x prime in the domain such that their corresponding outputs are equal. Because you see, for the function to be one-to-one, this is precisely the thing that should not happen. So if this is happening, then the function is not one-to-one, and conversely. Okay, so next we come to the definition of onto functions. Onto function. A function f from x to y is said to be onto or surjective if for every y in the range there exists an element x in the domain such that y is equal to fx. That means the outputs of f fill out y entirely. There is no element y in y that is not the output of anything in x. If that happens, then the function is not onto. Otherwise, the function is onto. So there must be some example for this also. Yes. So this is example 3.3.18. This is also informal. What is the example? Oh, again that same thing. The function f from the set of integers into itself defined by n square is not onto. For the function to be onto, what is the condition? If I choose any element from the range, any y from the range, in this case the range is the set of integers, then I must have an element from the domain which generates the element y as the output when the input is that element. Now if I choose any integer, do I have it as the square of some integer? Of course, that's not always possible. In fact, a counterexample can be easily produced. Note that for this element -1 in the set of integers, there exists no x in the domain such that x square is equal to -1. From elementary properties of real numbers, from basic properties of real numbers, that's why this example is informal. We know that the square of a real number is always non-negative. It cannot never be negative. So there is no such x. And if there is no such real x, then all the more so there is no such integer. Hence, we have already written it's not onto. However, if A is this set, it's the set of all squares of integers, then the function g from z into a given by same formula gn equal to n square is onto, because now in the range the things are squares of integers, so definitely the function will be onto. Just like one-to-one functions are sometimes called injection, onto functions are sometimes called surjection. So the notion of onto function not only depends on what the function does, but also on what its range is. Like all one-to-one functions depend on the domain, onto functions depend on their range. Okay. Then there is remark 3.3.19. Now there is some sort of duality between these two notions of one-to-one functions and onto functions, which is explored in these exercises. The concept of injectivity and surjectivity are in many ways dual to each other, and for this see these exercises, which we will see of course after this section ends. Three, 3, and 3, 4. Excuse me. And now once we have the concept of one-to-one and onto functions, we then next have the concept of bijective functions, combining these two together. This is very important. The others are also important, but this is more important. Bijective function. That is both injective and surjective is called a bijective function. It has to be both injective or surjective, and this has another name, bijective function or a bijection or is called invertible. Let me write it here. Okay. Now next we have an example.